So welcome to yet another tutorial at Programming Knowledge, and this is going to be a very interesting tutorial. So today we are going to learn about Sieve theorem. So this is a very important theorem, a very important one, and so basically it helps us to generate all the prime numbers up to n in a time complexity of n of log n. So basically we are going to generate all the prime numbers in n star log n time complexity. So we are going to cover this. So before this, what could be the we can let me start with what can be the approach you want to have, like a basic approach. You can like a basic approach. What first approach comes in your mind? So I'm going to discuss why we are going to use this theorem instead of a naive approach. So basically, the what basic approach you have, like if you want to generate all the prime numbers up till n. So for every, like for each number from 1 to n, you would traverse. Okay, so you traverse. So this is the first approach. So you would traverse and check check for every number. It is a it like for every number, is it a prime for every number, and check for every number if it is a prime. Okay, so you can check prime basically. I want to tell you that you can check prime in like we have so you can check prime in root n complexity, that is square root of n complexity. So time complexity of your this approach becomes like for n star, and then like if you check if it's a prime, then you will print that number. Okay, you will print. Okay, so basically we will do the analysis of time complexity. So this part takes time complexity of n. Okay, big O of n. Okay, and this part takes time complexity of square root of n. Square root of n. Okay, now, and this, your print statement takes time complexity of O of 1. So this is constant. So constant. So this is a constant because O of n takes linear, then square root of n, then O of 1. This is a constant, so basically you can ignore this. This is not an issue. Okay, you can ignore this. So print statement doesn't take any time complexity. So your approach for this would be n star root n. So this is your approach. And for a very large number, there might be a possibility that root n tends to n, then it might take n square, but this could be the average case complexity of n star root n. And we can have a better approach. We can have it do this in n star of log n. Okay, so this is much more better approach. So how we are going to do that? So for this we are going to learn the first, going to have a glimpse of theorem what we are going to do. So basically we are for n is equal to 50, we are going to generate a list, but I have typed the list in this such a way that I can divide it and explain you easily, but you would have all these number in an array, so that would be a list. Okay, and that would take a space so that would be an array would take the space. Okay, so you would have these n numbers in an array. Now, so basically the first base case would be that 0 and 1s are not a prime number. So we would like these are our base cases, and we can solve such a corner case or base case we can do with a single if condition, that 0 and 1 are not considered as a prime number. So we would ignore them or would treat them as a false. Okay, then the first prime number is here is 2. The very first prime number here is 2, and the next prime number is 3, then 5, then 7. Okay, so basically what we are going to do, like uh, first if the first prime number is 2, so what we are going to do, that we are going to take every number that for the very first prime number, that is 2, for every number that is divisible by the first prime number, that is 2, and which is greater than equal to the square of it. So I want to say that first prime number is 2, and we would take all the numbers which are divisible by 2, all the numbers which are divisible by 2 and greater than equal to square of it. So square of and greater than equal to square of it. So 2 is the first prime number, square of 2 is 4, and all the numbers which are greater than equal to 4 and are divisible by 2 will be marked as false. So in this process, so basically in this process what we are going to do, we are going to mark them as false. So 4 is the first number which is going to go, then another is the 6, then 8, and then 10. In the same way 12 would go, 14 would go, 16 would go, because it is divisible by 2 and greater than equal to the square of 2, that is 4. 20 would go, hence all the numbers would go. 50 would go, 48, 46 would also go, 44 would also go, 44 would also go, then 42 would also go, and in the same way 40 would go, then 30, and these two numbers also, 28 and 38 also would go, then 36 and 26, 24, 34. So it might be a little time consuming process, but it's going to be very good for your understanding. 32, 22. Okay, so basically we removed all the numbers, and now the next prime number here is 3. So we would all remove all the numbers which are greater than equal to the square of 3, that is 9, and are also divisible by 3. So the first is going to go here, one is going to go is 9. 9 is divisible by 3, then 12 have already gone, then 13, then next is going to go here is 15. 15 would go, 21 would also go. Yes, 21 would also go. Then the next here is going to go 27. Yes, then the next is going to go 33. Go 33, 35, 39 is also divisible by 3 and also greater than or equal to square of it. 39 would also go. Then 45 would also go. Okay. Then I hope 41, 43. Yeah. Yes. Yes. Yeah. So the next prime number here is 5, and we would remove all the numbers which are greater than or equal to square of 5. So here the next prime is 5 and square of 5 is 25, so greater than or equal to 25. So we quickly jump here. So we would check all the numbers which are divisible by 5 and equal to greater than or equal to the square of it. So here we have 25. Yeah, gone. So almost we're done, and next prime number is 7, so we quickly jump to all the numbers which are divisible by 7 and greater than or equal to square of it, that is 49. So quickly jump here and we remove here. So let me check if the remaining numbers here are all the prime. So these are the base cases, so we would remove them. Yes, so now we are left with all the prime numbers. Let me check. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. 31 we have, uh, 31 we have, uh, and I removed to remove 35, because 35 was the case which was greater than or equal to the then square of 5, that was 25, and also divisible by 5. So I forgot to remove this, so you would be removing this in that case. 31, 31 we have, 37, 41, 43, 47. So I expect you that you must have got here that this is the basic approach we are going to have to learn here. So we will quickly code this, and it's going to be very interesting. So let's get started. So basically from math import star, you can import everything. Then you can have a test case. T is equal to int input, then while t. So basically if you have got the algorithm, you must be this was very necessary to understand. T is equal to t minus 1, Then I'm going to generate a function that generate primes, and I would take an integer n, and now I would generate primes is equal to, first I'll generate a boolean array true is equal to true star n plus 1. Now I'll do the base case primes of 0 is equal to false. This was the base case I had taken. I told you that 0 and 1s are not a prime number, so we can take them. Primes of 1 is equal to false. Now for I in range, the first prime number is 2, then int sqrt n plus 1. So if primes of p, so here you can take, let me take this as p variable, so this will be easy. If primes of p is equal to true, that we are going to consider that if it is a prime, like we took the first case, very first case of 2, then we are going to cancel all the numbers which are divisible by 2 and greater than equal to the square of 2. So for that we are going to do, for I in range p star p, okay, and n plus 1, and we would skip this. I know for the range function, this is the start end, and the, like, this is like p, so this is like I is equal to I plus p, like what we do like in C++, for I is equal to 1, I less than n, then I plus plus plus, that's increment by 1. So this is like increment, these are the steps, then primes of I is equal to false. So we have done this coding part. Now we would have a boolean array of true and false, so we would do for I in range 0 to len primes, if 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 it's a prime, if primes of I is equal to true, then we would print I with end is equal to. So basically this part, the logic part was up to this much was the logic part. This is the print function which is used to just use. I'm showing it to you to print. Okay, then I'll have n is equal to input. Okay, and then I would do generate primes. Yeah, so I hope I'm done with this part. So let me run this code. One test cases, and I will take the number 50. So yes, here you can see that I have prime numbers as 2, 3, 5, 7, 11, 13, 17, 19, 23. So let me check with this. I'll have a split window here. Yes, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. Yeah, absolutely perfect. So we had all these numbers. So I'll quickly explain that you had to do what you need to do. You need to have the very first number. Then if you check if it's a prime, then you would cancel all the numbers which are divisible by that. Like for the 2, like we did, like if it's divisible by 2, then we take all the numbers which are divisible by 2 and greater than equal to square of it. So here this was done by this part. So the total time complexity of this solution turns out to be n star log of log n. So this was a very good approach. So I hope you can implement on yourself and run with many such test cases. So thank you guys, thank you so much. Thank you guys, thank you so much.